All right, welcome to part 2 of this lesson. I just noticed that last one was an hour long. This one shouldn't be as long, I don't think, but I don't know. We're just explaining this stuff. The last one was a bit long because I had to explain what all these functions were, but we're just going to work 2 more problems, okay? Look, these are long problems, but I really hope you're connecting all the pieces of knowledge together. And I really like these next 2, in particular this number 3. Okay, so let's read this. Say the pressure of the air in the Earth's atmosphere decreases exponentially with the altitude above the surface of the Earth. So meaning, right, whatever the pressure is, as I get higher and higher and higher above the Earth, the pressure is decreasing because it says decreases exponentially, at least the pressure of the air. Okay. Okay, so it says the pressure at the Earth's surface, sea level. By the way, if you don't know what sea level is, that's 0 feet above. Okay, sea level is like ground level or whatever. That's what we measure. But this city is 5,000 below sea level, that kind of thing. Okay, sea level is about 14.7 pounds per square inch. We call that PSI for pressure. And the pressure at 2,000 feet is approximately 13.5 psi. So we want to write a particular equation. Again, notice particular equation, expressing the pressure in terms of altitude and using the exponential function y equals a times b to the x. Where this is a very basic function. We're not really given any guidance as to what the base should be. And so we're going to have to kind of create it, and that's why I think this problem is fun. So look, y is still your final amount. All right, so look, you've got y equals a times b to the x. Here's what we know. We know that the initial amount is 14.7 pounds per square inch. When I say initial amount, we're using that as initial because we're basically calling sea level the starting point. We are going to measure above sea level and we're going to measure below sea level. So x in this case isn't time. A lot of times it is time. In the last 2 problems it was time. In the next problem it's going to be time. But in this case, x is a distance, and in particular distance above or below sea level. So sea level would be when x is 0. You see, b to the 0. Making this our y-intercept, making this our initial value. Now, it does say that we're 2,000 feet above sea level. Let's say that's times b to the 2,000, because that's what x is, right? Equals 13.5 for y. Now, we want to figure out a particular equation, which means we need to figure out what b is. So we'll first start by isolating the exponential. We'll divide by 14.7 on both sides. We'll say this is 13.5 over 14.7 equals b to the 2,000. Now, how do we figure out what b is? Well, if you think about rational exponents, if you had 13.5 over 14.7 equal to b squared, what would you do? You'd take the square root of both sides, wouldn't you? Of course. And then you'd say that b is the square root of blah, blah, blah. And that would be your base. But look at that exponent. That's pretty big. That's like the 2,000th root of this number. Okay. So I don't even really know how to compute square roots by hand. I've seen it before. I don't really know how. 2,000th root. What? Okay, we could do that, but personally, I don't really like it. So I'm gonna play with it. I'm gonna say, screw that. I don't like it. I don't want to take the 2,000th root. I reject this notion. So we'll say, what are you going to do, Mr. Spink? How are you going to do this? Well, I want to figure out a base b, and I'm going to do some trickery here. I'm going to take the log of both sides. And you might say, okay, I'm with you, Mr. Spade. Let's take the log of both sides. Let's say log of 13.5 14.7 equals log of b to the 2000. Fantastic. Now, what base would you like to choose, Mr. Spade? Can I say, I like it as it is. I think base 10 will be sufficient. I'll explain in a second why. So let's just go with my reasoning for now. I say log of this equals log of that. Now, using power rule, we should deduce, right? So I'm gonna do a little arrow up here. Power rule suggests that this log of 13.5 over 14.7 equals 2000 times log of b. Now, real quick thing here, guys. Why am I not calculating 13.5 over 14.7? It's not a nice, pretty decimal, and I'm going to preserve the accuracy of this estimation or of this model if I just keep it like that and put it in a calculator. Okay, preserve the accuracy. Now I want to isolate that logarithm here, so I'll divide by 2,000. Let's divide by 2,000. And instead of expressing this as one giant fraction, I'm going to just use over 2,000 as a coefficient. I'm going to say 1 over 2,000 equals, 1 over 2,000 times this logarithm, log of 13.5 over 14.7. This equals log of b. Now that I've got this, I'm going to convert. I say, let's convert to exponential. I say, what? How? Well, the base is 10, and the exponent is that. What? What? The base is 10, and the exponent on 10 is 1 over 2,000 times log base 10 of 13.5 over 14.7. And that is B. Boom. Got it. Done. Did it. All right. Now, let's go back to what I said earlier. Why did you choose base 10? Well, base 10 is really nice units of measure, especially if we're in the metric system, which sadly in this question we're using the customary, right, the American units of pounds and inches and things like that, which is fine. It's acceptable. It's good. But we do kind of like the metric system because of base 10, right? 100 centimeters, 1,000 meters, right? 10 kilometers, right? This kind of thing, right? The metric system works wonderful with base 10. And even though I'm using, feet and miles and stuff like that, I'll still stick with base 10 because we're going to be talking about thousands of feet in the air, right? Maybe like the next question, look, it's 29,000 feet. Base 10 is going to be really useful for that. At least I would say. So, okay, what's our function? Well, our function is, right, now that you found B, I say, therefore, y equals, A is still 14.7, times B, this is 10 to that, I got to write small here, 1 over 2,000 times, not natural log, sorry, log of, is it 13? 13.5 over 14.7. All of this raised to what power? X. Yes. Let me take this, move it down. That's our function. Now, you might say this, Mr. Spake, why don't you just calculate that and put a decimal there? Well, You can do that. However, your decimals better be accurate. They better be stupid accurate, because this is going to matter a ton as we are dealing with thousands of feet, and in particular, lots of miles. So maybe tens of thousands, hundreds of thousands of feet, things that kind of like that, right? That's my function. And yes, it looks nasty, but that's what it is. By the way, I think you technically could clean this up as 14.7 times, you see log to this, should just be 13.5 over 14.7 times 10 to the 1 over 2,000. I don't like that, though. And you say, Mr. Spake, why don't you like that? Because 1 over 2,000, that's still this 2,000th root of 10. And I don't like that. You say, well, why is that any better? I say, just because it's a coefficient on a log, rather than a power, doing a root. But whatever. This is just Mr. Spake. Okay? And this is what his intuition tells him. This is what his intuition says the function should look like. And that's what we're going with. All right. I don't know. If you want to leave a comment, say, Mr. Spake, I think you're totally wrong, and I think the function should look like this. Absolutely leave a comment. I'd love to hear it. Okay? Even if you're not one of my students. Even if you're just a fellow stranger on the internet. Okay, part B. Let's predict this pressure. Now, wow, Mr. Spake, there's so much to calculate. Oh my gosh, I don't want to do this. Well, guess what we're going to do? We are going to store B equals blah, blah, blah in the calculator. What? What do you mean? Observe. We'll go to calculator. We're going to clear out this. The value of B is 10 to the power of, we made a fraction, 1 over 2,000 times log of 13.5 divided by 14.7, right? That was it, right? Okay. Now, instead of just clicking calculate, which by the way you could do, let's say, look, there's your calculation. It's 0.999957, right? If you round that to 1, shame on you, because we've established that the base is never going to be 1, otherwise you don't have an exponential function. And if you round that to 0.9999 and forget the rest of the decimals, you're gonna mess up your calculations. They're not going to be accurate. So here's what we're going to do. I'm going to enter this, right? But I'm going to store it into alpha B. Do you see how I press that? I'm going to press it again for you. Store it. I click the alpha, and then on apps button, it says there's a green B above that. I'm going to click B. Alpha B. Enter. Now, yes, it outputs that decimal, but what it's doing in the calculator is it is storing that exact value for B. Exact. Not a decimal approximation, that exact value. And that is going to be useful in our calculations. Okay? So look, we've stored that. And we're going to round our answers to 4 decimal places. This is where this actually becomes quite easy. You say y equals 14.7 times B, this is our calculator B, to what is the exponent? 29,000, right? X equals 29,000. That is the exact thing you're going to type into your calculator. Exact. So we're going to go to our calculator. We're going to type 14.7. And then it's open parentheses. We'll say alpha B to the power of 29,000. Boom. Got it. There it is. 4.276, and round that to 2. what did I say? 2762. Is that right? Okay. And of course, keep your measurements here. This is a pressure, so it's PSI. That's our answer. Boom. You got it. Do you see how we only had to type that ugly mess one time, but then we stored it for our base and we're good? We made a calculation. Thank you, calculator. Now let's do the next one. Let's say the edge of space, which NASA defines to be 50 miles up. So this will be 14.7 times our base B to the, 50 miles, but we have our x is in terms of feet. So we're going to multiply that by 5,280. You don't really need to do this, but my high school teachers made me do this. There are 5,280 feet in a mile. It's acceptable if you don't memorize that fact, but honestly, I have, since memorizing it, I've used it quite a bit just in normal life, just because, how many feet is that, Evan? And I say, oh yeah, well, I don't have to Google it. I can just do it for you, right? There it is. So I don't know. If you want to just commit that to memory, you'd look smart, okay? 14.7 times, we're going to do, times alpha B to the 50 miles times there are 5,280. That is not that. 5,280 feet there. And I get this decimal, 0.00019. So I know that it said, what did it say, 4 decimal places? I'm going to say 0.00019. I'm going to do 5 decimal just because I'd like. Okay? But if you want to do like the problem said, the 4 decimal places, say 0.0002. Okay. And that is the pressure 50 miles up. Notice that's practically nothing, right? The air pressure is extremely thin there. There's almost no pressure at all. At least, pressure per square inch or whatever. Okay. So let's do some more stuff. Human blood at body temperature will boil if the pressure is below 0.9 psi. Bet you didn't know that. And at what altitude would your blood start to boil if you were in an unpressurized airplane? So, sorry, if you've ever fantasized of jumping from space to Earth, I think at some altitude your blood's going to start to boil. Sorry. No unsafe skydiving of that nature, right? You're going to need a pressurized suit or something to regulate that. Otherwise, of course, we got to figure out how high above the ground this is. So here we go. Oh my gosh, the app is not responding to my touch. Okay, below 0.9 psi. So we want to figure out where is that, right? At what altitude is there a pressure of 0.9 psi? Because that's when we're going to get dangerous. We're going to start blood boiling, right? So we say y equals 14.7 times b to the x, right? And we're going to plug in y. That's 0.9 equals 14.7 times b to the x. We'll divide both sides by 14.7. So we'll say 0.9 over 14.7 equals b to the x. And then we'll just convert to log. So, look, you've isolated this. So you just say log base b of 0.9 14.7 equals x. And that's all you got to type in your calculator. I gave a lot of space here when there really didn't need to be a whole lot of space. So let's just do that. I go here, I say math. I scroll down to log base. I've stored that value for b. I move over here. It's 0.9 divided by, 14.7. Boom. Got it. 65,600. I'm just going to round like that to the nearest foot. So roughly 65,600 feet. Yeah, I'll do FT just because. FF, no, not fortissimo forte, just FT. Okay, and there it is. Now it says consider this length in miles, right? So again, 5,280 feet in a mile that means you're going to take your 65,600 and divide that by 5,280 feet to get a rough estimation for miles, right? So I'm going to say that this is roughly, let's just do that calculation. Let's divide this by 5,280. 12.42. I'm just going to say 12.4. That's about 12.4 miles. All right? So, 12.4 miles above sea level, and your blood is going to start boiling. Not good. Not good. All right. Last part, D. The Mediterranean Sea dried up about 6 million years ago, leaving a valley 10,000 feet below sea level. So supposing you were to go down into this valley 10,000 feet, what would the air pressure have to have been at the bottom of this valley? Well, this is actually pretty simple. Y equals 14.7 times, that's our base B, to the, well, what is X? It's 10,000. But it's not 10,000 feet above, it's 10,000 feet below. So I make that a negative. And I guess it doesn't give us any guidance on rounding. Maybe we'll do 2 decimal places. We're just going to do 14.7 times B. Whoa. Times B to the negative 10,000. I get 22.50. So I will say that. 22.50 psi. How much pressure is that? I don't really know. I don't know a whole lot about PSI personally. I'd have to look it up a little bit more to understand how heavy that pressure is. I don't know how heavy that is. I don't know. But we could look up together maybe. Maybe if you're curious. Look up. What the heck does that mean? Is that a lot? Is that a little? Is it like way too much? Would your body explode? Like, would you just crush? I don't know. We'd have to look that up. And there you go. There's that problem. Oh, I like that. That's fun. Yes, the base is complicated, but you stored it in the calculator and you never wrote it again. You just typed B and you were fine. So the hardest part maybe was part A. Okay. Let's move on to number 4, and this will be the last one for our video on this stuff. I know that this is long. I don't know how this is going to work in class, but we're going to make it work because these problems are worth our time. All right, number 4. You accidentally inhale some mildly poisonous fumes. That could happen to anybody, right? Especially in America. 20 hours later, you see a doctor. From a blood sample, she measures a poison concentration of 0.00372 milligrams per cubic centimeter and tells you to come back in 8 hours. On the second visit, she measures a concentration of 0.00219 milligrams per cubic centimeter. Let T be the number of hours that have elapsed since your first visit to the doctor, and let C be the concentration of poison in your blood. And then we're going to assume that C varies exponentially with T. So we're going to use 2 models here. Notice, look at the models we've talked about so far. We've used this one. We've used exponential growth decay. We've used compound interest and continuous. The things we haven't used yet are the decay function and the half-life function. And I told you earlier in the first part of the video, a half-life function is a decay function. But they have 2 different kind of uses or maybe contexts that we're going to work in. Okay? So the first thing, we're going to use the general decay function to write a particular equation modeling this. I'm going to flip my page, follow along with my key here. Okay. Now, this is going to be a bit of ugly writing, but it's okay. It is just because we have these nasty decimals. So, we say that A equals B, but I don't need to write all that again. It's right there. Okay, you can see it. The final amount. So look, your initial visit is this, 0.00372. So I know that the P being the principal value would be 0.00372. And you say, well, this isn't principal, Mr. This isn't money. This isn't investment. Fine. But that's, if you'd like, it's poison. Right? P in this case is poison. That's just a kind of a coincidence, right? We could use any substance or drug or, whatever that's in your system, but it just so happens P is poison. Okay. 1 minus R. We don't know what the rate is, but we do know that after 8 hours, T being 8 hours, we're going to measure this with T being hours, because it says that right there, that the final concentration in your blood is 0.00219. Okay. So our job is to find R. So, of course, naturally, we'll start by doing division. 0.00219 divided by 0.00372. You might say, Mr. Spake, can we calculate that? You're going to get a nasty decimal that you're going to be forced to round. Don't do that yet. Keep that accurate answer. If you don't keep that accurate, like super accurate, your patient could die, right? You don't know. We need to carefully measure the amount of poison and think about, how might we cure this or what do we need to do? We need that answer to be accurate, because if we're off by 0.01 milligrams, maybe something bad's going to happen, right? So we want to keep that accurate. So say this is 1 minus R to the 8th. Now, how could I get rid of this? You say, well, take the log of both sides. Well, we did that in the last problem, correct. But that's because I didn't want to take the 2,000th root of something, because that just seems ridiculous to me. An 8th root isn't so bad, though. I think we can take an 8th root. So that's what we're going to do. All right? We're going to say an 8th root of this junk, 0.00219 over 0.00372. That equals 1 minus R. Okay? Which means, I say therefore, right? Therefore, R equals 1 minus the 8th root of this junk here. 0.00219 over 0.00372. And just like the last problem, we're going to store this for R. We're going to store this for R in the calculator. And I'm going to make a quick note. Note, R is approximately. Just to make a note, because we would like to know what percentage is this roughly decreasing per hour, right? So let's do that. I'm going to go over here. We're going to do 1 minus, we got to use the nth root. We're going to use 8th root of, the first decimal is 0.00219 divided by 0.00372. And by the way, I can calculate that. I get 0.0641. 06. So that's about 6.41%. Okay? Roughly. This is just to tell us something. But like I said, don't round this. Okay? Please, please, please don't round this. We want our answer to be accurate. Okay? In science, you are going to round, and if you've taken chemistry, you've probably talked about significant figures, right? Oh my gosh, I cannot spell. Significant figures, sig figs, right? If you've talked about sig figs, you understand, right? There's a safe point for rounding, depending on what we're dealing with, right? And you can talk about that in chemistry. You can talk about it in physics, whatever. It's a science thing. I don't want to talk about it here. There is a way to properly round, but because we're in Algebra 2 class, I want our math answers to be as accurate as possible. As accurate as possible. So we say A equals P times 1 minus R, right? Well, R is 1 minus all that blah, 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 blah. So 1 minus R is 1 minus 1 minus blah, 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 blah. Does that make sense? So the ones cancel, and you're just left with that 8th root business. Okay? So I'm going to say, therefore, your function A for the amount of poison in your system, we still have to use that initial value of 0.00372, but we will say that 1 minus R is the 8th root of 0.00219 over 0.00372 raised to the t. And that's our function. If we're going for ultimate accuracy. If you take a science course, they're going to not leave it like that probably. They're probably going to teach you how to make that calculation, well, to do that calculation, and then how to round it accordingly. Okay? All right. Now, let's make some predictions with this, right? And by the way, whether you store this for R or whether you store this for B is kind of up to you. In fact, we're going to use 1 minus R so much. Let's just do, I'm not even going to store for R. This is going to be our base, right? That's our base, B. We're going to store for B in calculator. Again, we're just going to do that. So I'm just going to go ahead and do that. All right? I'm going to get it out of the way. I'm going to retype this. I'll delete this 1 minus business. Goodbye. Goodbye. And you, my friend, are going to get stored for B. You're going to be my base. Good. Good, 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 good. Love it. All right. The doctor says you might have some serious body damage if the poison concentration was ever as high as 0.015 milligrams per centimeters cubed. Or it's not milligrams, right? Oh, it is. Okay. Based off your mathematical model, was the concentration ever that high? Justifies your answer. Okay. Well, let's see. We want to see, was the final amount ever that high? Now, you say final amount. This is interesting. You got to go back in time here, right? In this case, we're making a prediction about what the level of poison was prior to our check-in with the doctor. So our check-in with the doctor is later after we've inhaled this poison. And if you go back to the problem, it says that you inhale these mildly poisonous fumes, and then 20 hours later, that's when you go see the doctor. So what we want to see is the true initial amount of poison in your lungs or whatever, right, in your body. We didn't have a doctor right with us with a tool to measure that in our blood, right? So we're going to use time equals negative 20 to go back from when this happened. So let's do that. So A, right, our final amount is going to be 0. I want red. Actually, I want blue. I want blue instead. 0.015 equals 0.00372 times B to the T. And see, B, I'm going to use that base B as the value that's stored in the calculator rather than writing that 8th root of blech. Yeah? Okay. So then divide both sides by the A value, or the initial value. So I'm going to get 0.015 over 0.00372 equals B to the T. So then how do I figure what the time is, right? Well, actually, I just realized that we could have done this two ways. Okay, I'm going to continue with this way because I'm already on it, right? But actually, I had originally planned to do this a different way. So let's say this happens, right? Then that means t equals log base b of this value, which this is going to tell us how long ago we would have ingested the fumes, if that's the case. So we're going to type that in. So I'm going to go to my calculator. I'm going to say math log base b of, what was it? 0.015, 0.015 divided by 0.00372. Negative 21, and some other decimals, but this is roughly 21 hours ago. And we ingested these fumes 20 hours ago. Does that make sense? So if, like, this lethal amount, or concerning amount, I should say, if we're backwards engineering this, if it was 21 hours ago or further since we inhaled the fumes, then that means we would have inhaled that that bad amount of fumes. So this is one way, but I actually don't really like this as much as the other way. It's actually much more straightforward. So I'm actually erasing all that beautiful work and just going to do it this way. You first inhaled it 20 hours ago. So let's just take that. Look, your final amount, or in this case, your A is kind of like your initial, right? As 0.00372 times your base to the negative 20. You say, why are we doing to the negative 20? Well, because it's 20 hours before you first checked into the doctor. So we're going to type that, 0.00372 times your base to the power of negative 20. Did I do that right? Yeah, okay, I did that right. 0.0139. Let's be super accurate here. This is roughly 0.0139 891. 891. I'm just going to use a bunch of them, right? And that concentration, right? If I compare this to, what is that, 5 decimals? So 1, 2, 3, 4, 5. So we could call that roughly 0.014. Yeah, because if you start rounding up, 1, 2, 3, 4, 0, 0. That's our concentration to 5 decimal places, which is less than 0.015. Yeah? If you want, I'll erase those. So that means in our system, we had about 0.014 concentration of this poison, and this would be serious body damage if it was at 0.015. So it looks like we're okay. We're going to say, it looks like we are okay. I'm going to box that, because that really is the answer. Right there. When we inhale the fumes is less than what the doctor is saying would be the bad thing. Okay? Okay. Now it says you can resume normal activities once it's dropped to this. How long is this going to take? Now this is going to be the exact same setup as what I had done the first time around on the previous problem. You say your final amount is 0.0001, and then another 0, equals 0.00372 times b to the t. So look, right, you're going to divide by this. You're going to say 0.001, there's 3 zeros, careful here, 0.00372 equals b to the t, which applies. You do logarithmic conversion, right? T, your time, equals log base b, where we've stored b in a calculator, of 0.0001 divided by 0.00372. And what is that, right? What is that time? Well, that's what the calculator's for. Math, log base of b of, what do we say? 0.00372. 54.6. Yeah, and that's the answer I've got here as well. This is roughly 54.6 hours. Rough estimate. Okay. See how I'm rounding my final answer to give you guys like we are telling our audience the information rounded, but we're not rounding while we're doing the calculations. This way, our answer is guaranteed to be accurate. Okay. We're almost there. I know these are long videos. I'm sorry. But aren't they interesting? Aren't these fun? Okay. The biological half-life of the poison is the length of time it takes for the concentration to drop to half its present value. So we want to find the biological half-life of this poison, meaning we want to find the time it takes for this poison to decay to half of what it was. So if you think about this, essentially, you want your final value to be half, right? You want final amount to equal 1/2 initial amount. So think of it like this, right? If I set up my equation, A equals 1/2 P. This implies that A equals, we're using this model, right? B minus 1 minus R to the T. We're not even really doing that, are we? Right? We're doing B because we stored B. But if A is 1/2 P, then this is 1/2 P equals P times this. And if you divide both sides by P, those cancel. And so really what I have here is 1/2 equals this 1 minus R to the T. But look, 1 minus R is what we stored for B in calculator as a base, right? So really, so we can rewrite this as 1/2 equals our base that we've stored in the calculator to the power of T, which implies that the time T equals log base B of 1/2. Does that make sense? I hope that does. That component might be a little bit better said for class. But essentially, like, you know that the ratio of the final amount to the initial amount needs to be 1/2 because you're looking for the half-life, right? So we don't even have to half the initial amount. You can. Look. This is what I'm doing, guys. 0.003712. Divide that by 2. That's the left side. Now divide the left side of the equation by the right side, which is 0.00372. Oh my God, it's 0.5. It's a half. Duh, right? Duh. Okay. There we go. So log base B of a half. We're just going to do this. Log base. Whoa, that scared me. Oh my God. Stop. Oh my God.
But did you know?
Hello? What's happening? Hello? Oh my God. Oh, Okay, I don't know if you can still hear me, but an ad started playing on my calculator app, and I freaked out. Oh, my Lord. I think I clicked the ad. Oh, scary. Okay, where were we? We said math log base b of 1/2. 10.466 hours. So this is roughly 10.466 hours. And I'm going to generalize this because here's the thing about half-life is it's rounded pretty liberally, I guess you would say. We're going to say that this is roughly 10.5 hours. Okay? This is your first introduction to Half-Life, probably. But the exact time doesn't have to be that exact. And we can explain that in a little bit. Okay? But there you go. It's about 10.5 hours. That's about the half-life. So let's write the particular equation of this form of the half-life formula. Here's the thing. For this one, we're not going to be exact, and that's okay. We're not even going to do this 10.466. I'm straight up going to say that the half-life is 10.5 hours. So I'm going to say A equals A naught, the initial. There's still that 0.00372 value, times 1/2 to the T divided by the half-life, HL, is 10.5 hours, which I'm just going to write as T divided by 10.5. Done. I ain't even going to worry about it. I ain't even going to sweat it. And there you go. All right? Okay. Now, why? Right? Why, Mr. Bate, you've been making this big deal about not rounding your answers, especially not rounding your functions, right? But here you are being hypocritical and rounding your half-life function. Well, half-life is different a little bit. Giving an estimate of 10.5 hours for this decay, it's kind of hard to measure this blood rate, this poison rate, instantly, right? I mean, unless you're taking the thing every minute, right? But it takes a while to do blood analysis, right? It's not, you can just prick your finger and get instant data on all the things wrong with you, right? It takes time to do blood analysis, and so that kind of thing isn't always super accurate anyway. It's accurate enough to get a sort of health estimate of what's happening with you. But trust me, this is sufficient to say that 10.5 is the half-life, rounding this way. I wouldn't go as far as saying 10. It's not 10 hours. I'd still strive for accuracy. And of course, if you want to be very accurate, use log base b of 1/2. But that's not really how the half-life formula is used. Half-life is a time value. And from what I've seen, it's usually, it can use decimals. Like, see here, I use 10.5. And maybe it does about 2 or 3 decimal places. So if you want to round this to 10.47, that's totally acceptable. That's great. That's good. And you can totally put 4.66 here, right? It's fantastic. That's just what I'm doing now. I'm saying, you know what? It's about 10.5 hours, and there you go. Okay? All right. For this last part F, it says use a search engine, aka Google or Yahoo. Who uses Yahoo, right? Or DuckDuckGo or whatever that is. I don't know. I guess some people use that. I don't know who they are, though. Use a search engine to answer. Why would you prefer to model this scenario with a half-life equation instead of using the general model of exponential decay? Yeah? Like, if this is my ultra-accurate thing for the poison in my blood every hour, right? Which is good, a nice estimate. And it's exact. I can tell you exactly this stuff. Why would I use this? Why would I look at the half-life of this? And why would I round this half-life so liberally to 10.5 and not be so picky about this rounding, right? I leave this for you to investigate. I will post the key at some point to this last part, but I want to see what you come up with. Why would we use a half-life equation for this? What even is this thing? Why do we use this? Because exponential decay, right, it tells the same story. It's all about decay. Half-life equation is exponential decay. Why? Why use this? And that's your question to answer. Thank you for watching this video. I hope you found it informative and helpful. And if you have any questions, please just let me know. This is a lot of stuff, guys. And not only is it quite a bit of algebra, this is a very general overview of the sciences of business and economics. I mean, we are tackling multiple disciplines in this sort of worksheet here. You're looking at a variety of different career paths. Maybe your career path doesn't use half-life ever, right? But maybe it uses principal amounts and investments and stuff. Or maybe it uses, talking about pressure, PSI, and stuff like that. So there you go. Okay, again, thanks for watching. I'll see you around.